Chemical equilibrium, part 2. The relationship between kinetics and the equilibrium constant K. Okay, so let's remind ourselves of something we learned during our kinetics unit when we talked about kinetic mechanisms with a fast equilibrium step. And we talked about what a fast equilibrium step was. We said it was a reversible reaction. The forward reaction, where A goes to B, has a rate constant K1, so it happens at some rate with this rate constant. The backward reaction is B going to A with rate constant K sub minus 1. Now, let's apply this to our example. So our gas phase equilibrium. So we have been talking about nitrogen dioxide dimerizing to form dinitrogen tetroxide. And this is a reversible reaction. So for our reaction, the forward reaction is nitrogen dioxide going to dinitrogen tetroxide, and the reverse. The dimer splits up into nitrogen dioxide. Let's write the rate law for the forward reaction and the backward reaction in our equilibrium. I've added rate constants, so K1, K sub minus 1 for the forward and reverse process. So let's write the rate law for the forward reaction. It would be rate is equal to K1, so there's K1, rate constant K1, and nitrogen dioxide to the second power. So that's the rate law for the forward reaction. The rate law for the backward reaction is rate equals K sub minus 1, so the rate constant for the back process, the reverse process, and dinitrogen tetroxide is the reactant for that reverse process. Here's the difference. When we talked about kinetics, we talked about the beginning of the reaction, measuring rates of reaction, where the forward reaction rate was much faster than the back reaction rate. The only exception was when we talked about that fast equilibrium step. But at the beginning of any reaction, the forward reaction rate is faster than the back reaction rate. So that means that reactant is converted to product faster than product is converted to reactant, and that's at the beginning of the reaction. And so that's what we're seeing here. We're seeing nitrogen dioxide being converted to dinitrogen tetroxide, and we are seeing this partial pressure buildup of the dimer, and all of this is in time. So this is the same plot we saw in the previous part of this equilibrium discussion. And remember, at equilibrium, when everything's stabilized, we had 0.5 atmospheres of nitrogen dioxide and 0.25 atmospheres of dinitrogen tetroxide. Here's the way to understand what's going on. So when we talked about kinetics, we talked about this early time. And when we talked about the method of initial rates, we talked about a really early time. So right at the very beginning of the reaction. And what we didn't really talk about was at the very beginning of the reaction, there's very little contribution from the reverse reaction. So essentially, we're measuring the forward reaction rate. Now, once we let the reaction run, so we reach this part of the curve where the concentrations stay constant. So constant in time. At the early part, partial pressures are changing rapidly, and once we reach equilibrium, they're just constant. So this is the equilibrium part of the experiment, and this is the kinetics part of the experiment that we discussed in Unit 14 in earlier videos. What is really going on at equilibrium? And basically, once this reaction is at equilibrium, the forward reaction rate is equal to the back reaction rate. So that means this rate for the forward reaction is equal to this rate for the back reaction. So those reaction rates are equal. That's what we know at equilibrium. Both of those processes are occurring microscopically at the same rate. But it still looks like macroscopically, or what we can measure, nothing is changing. So let's use this reversible reaction to derive something called the equilibrium constant. This is going to be a very, very important constant in this chapter. And so what we're going to do is we're going to set the forward reaction rate equal to the backward reaction rate, just like we did in the kinetics chapter with the mechanisms involving a fast equilibrium step. So the rate of the forward reaction, and that's equal to the rate of the back reaction. Okay, so let's solve for this ratio. So I'm going to start by dividing out this term. Okay, so we're going to divide both sides by nitrogen dioxide to the second power. Once we've done that, we've canceled those out. So now nitrogen dioxide is in the denominator. Now we're going to divide out k sub minus 1 on both sides. And when we clean it up and cancel out those reverse rate constants, then we're going to end up with K1 over K sub minus 1 is equal to dinitrogen tetroxide divided by nitrogen dioxide to the second power. Now, this ratio, K1 over K minus 1, that is equal to the equilibrium constant K. So what we're doing is giving it a new name. So this ratio of rate constants, the forward rate constant divided by the back rate constant, that is given a new name, and it's now called the equilibrium constant K. And this is the fundamental relationship between kinetics and equilibrium. So the equilibrium constant K is the ratio of these rate constants. So from now on, we're not going to write those anymore. So instead of writing K1 over K sub minus 1, we're just going to write the equilibrium constant K. So let's summarize what we've learned so far. So we have a lot of concepts, and we're going to get a little bit more into the nitty-gritty about the equilibrium constant in the next video. But let's remind ourselves of what we've learned. So at equilibrium, macroscopic observables have stopped changing. So that means it looks like nothing is happening. Now, at equilibrium, there's a balance between the forward reaction rate and the backward reaction rate, or the reverse reaction rate. So those rates are equal. They're balanced. The equilibrium state is completely independent of the initial concentrations or partial pressures of reactants and products. So remember, that means we can start with all reactants or all products, and we're always going to end up at the same equilibrium state under a given set of experimental conditions. And also remember that the equilibrium state does not depend on reaction rates. So the reaction can go slowly to equilibrium, or it can go quickly to equilibrium, but either way, it's still going to equilibrium. So it doesn't matter if it's fast or slow, it's going to equilibrium. And the equilibrium state does not depend on how fast it gets there. Okay, so next up, we're going to discuss the law of mass action, and that's in part 3.